still hidden somewhere. Anyway, so thanks for the invitation to come talk. Thank you guys for being here. So I'm going to, well, talk today about some methods for large-scale optimization. Perhaps a better title for this talk would be interesting sort of models of optimization problems that we can leverage to solve more efficiently. All right, and I'm going to divide the talk into two parts. The first part will be sort of convex optimization. Also, I'm going to try to use this to write on the slides, so we can ask questions and doodle and stuff like this. So the first part will sort of be on more convex optimization, and much of this stuff is likely familiar, and it's certainly fairly well-known things. And I'll talk about a few sort of problem structures that are more and more common in machine learning that we've sort of developed techniques to attack more efficiently. And then in the second part of the talk, I'd like to talk about some sort of non-convex optimization problems, right? And specifically, I'd like to sort of dig down and understand, what are the structures in non-convex optimization that we can leverage to develop interesting methods. And I'll also talk about sort of a growing understanding that if you have data coming from some kind of reasonably nice statistical model or statistical process, then often the sort of resulting optimization problems are easy. They're just not that hard. We can solve them efficiently and provably and things like this. Okay, so that's going to be the second part of the talk. Given that this is a tutorial and a reasonably small audience, feel free to interrupt at any point and just ask questions, whatever you like. Okay, so let's start with the beginning. So the problem that we're going to look at, I'm going to be an optimizer today. So my variable through this whole talk will be x. All right. So x is not data. X is the optimization variable or the decision variable. And usually we will be looking at. So this is optimization variable. Usually we will be looking at stochastic optimization problems. So specifically, I will write things as f of x is the expectation of some loss function f on our optimization variable x, and s will stand for sample, okay, or sample data point or something like this. So this will be the sample, and this is our instantaneous loss. Okay, so these are the types of problems that we're going to be thinking about mostly today. Okay, and there's sort of course, millions and millions of examples of these. The standard one would be linear regression, right? So in this case, and we'll set some notation that we'll use for the rest of the talk. So in linear regression, you have the sample S is usually a pair A-B, where A is in Rn and B is in R, right? And then the instantaneous loss that you have, of course, is equal to just 1/2 A transpose X minus B squared. All right, so, and this is how you know I'm being an optimizer because we're using A and B for data. We could switch to, X and beta and Y, but whatever. We'll do with A and B will be data, X is going to be variable. Okay, so let's start by just going over some basics of convex optimization. So for this first part of the talk, I'm going to be focusing on convex optimization problems. So actually, can I get a quick show of hands? How many of you are familiar with, just so I know the audience, how many of you are familiar with subgradient methods and things like this? And how many of you are not? Okay, so a few of you. So Marty, apologies. Essentially all of the basic proofs that I do, Marty did in 2002? 3? When was that paper?
2003.
2003, okay, so 2003. But anyway, we'll do this. So a function is convex, recall, if it's always sort of, well, if it's bowl-shaped, right? So f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y. Right? So that means you're convex, which means that your function is shaped something like this. And then anytime I draw, any line I draw above it, I can always just, any line between 2 points stays above the function. Okay? And we say a vector is a subgradient of a convex function if basically it forms a linear underestimator. So a vector g is a subgradient if it forms a linear underestimator of your function. So say, starting with this guy, if this is my point right here is x, then here's the function, y goes to f of x plus g transpose y minus x. All right, so subgradients are any line that just stays underneath your function and touches it. Okay? The simplest method in optimization, in convex optimization, is known as the, I apologize. Let's do a few examples of subgradients just so we've got some idea of where these things come up. So standard examples would be, say, the L2 norm. So for the L2 norm, the subgradient of the L2 norm is either the derivative, so this is equal to grad f of x, when x is non-zero, and otherwise it's all vectors that have 2 norm less than or equal to 1. And so the picture here, if I think of the L2 norm in R2, right, it's sort of a ice cream cone shape. This function right here is the 2 norm, right? So then anywhere that's not 0, the subgradient is just, this is a differentiable function, and so the subgradient ends up just being the derivative of our function. Whereas at 0, right here, every vector with norm less than 1 can go underneath this function and stay under it. Right? So these things may actually be sets, but they're usually the derivative if you're differentiable, and otherwise they're some kind of set of vectors that give you linear underestimators of your function. Another example would be the hinge loss. Okay, so this is a loss we often see in support vector machines, and in this case, if I draw the hinge function right here, so this is 1 minus t truncated at 0. Here's t growing, right? Then the derivative, the function itself is differentiable everywhere, except for at the point t equals 1, where you have a number of subgradients. Okay, and so that's what leaves you with this kind of subgradient calculation. All right, so now if you were going to develop a sort of a generic method for convex optimization, basically, what we do is what's known as the subgradient method. It's sort of the simplest method, and this is somehow what makes convex optimization easy, is that essentially you can solve any convex optimization problem by just descending on subgradients. It's not efficient, it's not fast, but it will converge. Okay, and so this is not a descent method. You can actually go uphill when you're following subgradients, but it will converge to the optima of our function f of x. And the reason for this is because you always basically get closer to optimal points. So let's draw a picture here. And think about what the subgradients are. So let's. So here's the level curves of, say, the L1 norm. Okay. So this, if you're looking at it, this is a function growing out of the screen towards you guys, right? And at any point, right? So what's the subgradient set here? It's just the vector pointing down this way, right? Whereas here, the subgradient set is anything that's sort of on this side of the space. But basically, all of these essentially at least point you a little bit closer to, all the directions from here point you a little bit closer to the global minimum of this function. All right? So subgradients take you closer to global minimum. They don't actually decrease your function values, but they do take you closer. And this is actually the insight of sort of the simplest proof in the world. So recall the subgradient method is just you have your iterate, you have an iterate xk, you choose any subgradient in the subgradient set of your function f, and then you follow that gradient direction downhill, or try to go downhill. And so this is basically going to be the only proof I give here, because this is a very simple method to write down. It luckily also has a very simple proof. And I think this proof, Marty certainly had this proof in 2002, so let's give credit to Martin Zajkovic, if you guys don't know him. So we'll give credit to him for this one. But it's luckily a fairly clean, straightforward proof. So all we're going to assume is that the gradients are bounded and that we are within some finite distance of the initial point. So let's think about how we might prove that this method converges. This is what shows us that convex optimization really is easy. So all we have to do
is look at the distance from xk plus 1 to x star. Okay? This honestly is like the entire proof. Right, this is all. If you remember one thing from this talk, at least on the convex optimization part, just remember that you look at distance to optimum. That's it. Okay, so this is the entire proof. But what is xk plus 1 minus x star? This is 1/2 xk minus alpha k gk minus x star squared. Okay? I'm just writing out the subgradient iteration. And then now I can just expand this square. So this is equal to 1/2 xk minus x star squared, so that's a good start. Then I have this intermediate quantity, gk transpose xk minus x star, and then I have this alpha squared gk squared. All right, and now so basically, if I look at this, right, so we've sort of shown that xk plus 1 minus x star is somehow related to this. So now what we want to do is show that these second two terms are somehow going negative, so we're at least going to converge or something like that. And that's actually fairly straightforward. So the key insight is that this is the subgradient of f, right, at xk. So recall that gk is in the subgradient set of f at xk. And so we have that this is now less than or equal to 1/2 xk minus x star squared minus alpha k times the quantity f of xk minus f of x star plus alpha k squared over 2 gk squared. All right, so the point is that if you are far away from the optimum, you make a lot of progress, and otherwise maybe you don't make that much progress, but that's okay, you're close to the optimum anyway. All right, and then once you've got this, now recall, sorry, we'll go back to this previous slide. We assumed that our function had bounded subgradients, which is not really a real restriction, and so now this is less than or equal to 1/2 xk minus x star squared minus alpha k times this gap, f of xk minus f of x star plus alpha k squared over 2 m squared. Okay, and then all we're going to do is we're going to just rearrange this, take this function value term, move it to this side, and then take this guy and move it to the other side. And then basically we're going to just have that the sum from I equals 1 up to k of alpha I f of xi minus f of x star is less than or equal to 1/2 x1 minus x star squared minus 1/2 xk plus 1 minus x star squared plus the sum of the gradients. Oops, sum I equals 1 up to k alpha I squared over 2 times the magnitude of our gradient squared. All right, so this is it turns out is basically the entire, this is a proof that the subgradient method converges. Okay, so this, remember, we did this basically in one line. I know there are more than one line, but it's one line, right? And that one line is just this. So you write out this and then you're more or less done, okay? And you follow your notes. And once we've got here, so then the sum, this sum, basically is bounded by your distance to optimality of your first iterate, and then this sum of squares. And so as long as this is finite, and the sum of the alpha i's is infinite, this will converge to 0. And so that's what this final guarantee says here, is that, this is exactly what I had just written. So then, if we take, say, an average of our iterates or something like that, then we get that f of x at the average by convexity minus f of x star is less than your distance. So sorry, I didn't define this. This is x1 minus x star squared plus this sum of squares. Okay, so if the sum of alpha I squared is less than infinity, I equals 1 up to infinity, and the sum of your step sizes, I equals 1 to infinity, alpha I is infinity, then this will converge. Okay, so all you need is square summable but not summable step sizes, you'll get convergence. Okay, and so now you guys are probably wondering, well, what's the, okay, good, what's the point of this? Who cares? So there are 2 points to this, right? So, whoopsie. So the first point is that, excuse me. Uh-oh. There we go. So the first point is that this analysis is really clean and fairly straightforward. The second point is that this method is really slow. Okay, so the convergence rate of this is just that it converges, which is all, which is not exactly what you want. But the third thing that's true, and we'll see this shortly, is that because this method is so dumb, it's incredibly resilient to noise, which makes it really great for a lot of machine learning applications. Okay, and we're going to see how we can leverage that shortly. So let me just give an example of this. So let's look at, come on. Okay, good. So let's look at a robust regression problem. So here I'm going to minimize ax minus b, the one norm of this. Okay, and so basically my subgradient is just, I look at the signs of my errors in ax minus b and I hit them with my matrix A. Okay, and I'm going to perform subgradient descent with different fixed step sizes and just plot the best objective value minus the optimal objective value. Okay, and I'm getting a lot of lag on this thing. Okay, and what we see is that basically with a large step size, so that's this green one, that's a step size of 10, basically you just jam and you make no progress. And as you decrease step sizes, your method gets basically closer and closer to having good performance as time goes on. Okay? I mean, because we have a fixed step size, we don't actually converge, but the smaller your step size is, sort of the slower the progress is that you make at the beginning, but at the end of the day, you do a little bit better. And this is plotting progress over time of our objective values. But I think what's the one thing to note here is that very quickly you make pretty good progress, and then you sort of stop making progress efficiently. Okay? But if you think about where might you apply these methods for statistical problems, maybe you don't need that much accuracy because there's already noise in your data, so if very quickly you can get to something good, maybe you can call it a day. All right. Now, let's take a step back now. So we've gone through this subgradient method, which I said, okay, this is a really slow method, da-da-da-da-da-da-da. So the reason we actually really like this method is because for a lot of the problems we have in machine learning and AI and things like this, is we actually can really efficiently compute random vectors that approximate the subgradients well. And so this gives rise to the projected the stochastic subgradient method, which the setting is that I'm given access to what are known as stochastic gradients of my function f. Okay, and what is a stochastic gradient? A stochastic gradient is just any vector, gk, such that in expectation it belongs to the subgradient set of f. All right. So when is this going to be useful? Well, it's going to be useful in situations where we can compute stochastic gradients much more quickly than we can compute the real true gradient of our function or the true subgradient of our function. So useful if this is cheap. All right, and the iteration here is exactly the same as the iteration of the subgradient method. Basically all we do, and I added one little tweak here, but basically we just, you say xk plus 1/2, say, is equal to xk minus whatever the step size you're using times your stochastic subgradient. And then I've sort of tweaked it a little bit here. I've said, let's suppose we have some constraints. So some constraints C. And then after our iter, we're just going to project our, this is sort of an intermediate iterate. After our iterate, we're going to project that back onto the constraint set. Okay, so pi c, c is equal to argmin of x 1/2 x minus c squared of x in my set C. So the picture is, if this is my set C, and this is, say, xk plus 1/2, and this is, say I started here, xk, I took a gradient step out to get to xk plus 1/2, I'm just going to project back onto the constraint sets right there to get xk plus 1. Okay? So I take gradient steps and then I jump back onto the set. And so let's think about where we might see this. So a standard example where we see such things is in machine learning problems where we want to minimize some empirical risk. Okay, so suppose we had a function f of x, which was equal to a very large sum of data points, right? Say, for example, this might be, I don't know, in the regression example, f of xs is equal to 1/2 ai transpose x minus bi squared, right? And then this is equal to basically 1 on n times the 2 norm of ax minus b squared, where a is equal to the matrix of a1 transpose through a capital N transpose. Okay, so these are the kinds of things, linear regression or logistic regression or things like that we see a lot. And here, right, so the true subgradient of this is just we take a subgradient of every individual term in this sum, and then we average out their subgradients. But of course, if I just pick one of these terms in this sum completely at random, and then I compute a subgradient here, what's the expectation of that guy? This is not a trick question. I'm actually asking you. I want to make sure we're awake and happy and stuff like that.
G.
What's that?
G.
G, right. It's the correct subgradient, right? Because the expectation of this guy is just 1 on n, sum I equals 1 to n of gi, right? But of course, the time, if n is 1 billion, the time to compute this is, it grows linearly with n. And the time to compute this is, you have to sample a number from 1 through n, and then you compute one gradient, right? So it's essentially 1 billion times cheaper to compute this than it is to compute this, right? So n times cheaper to do this. Oopsie. And this is where the power of subgradient methods really comes through, is because they are so dumb, basically they don't care if you use one random subgradient or all n of them. Right? And so we can really leverage this sort of summation structure or stochastic optimization structure to do things much, much more efficiently. All right, so let me give an example of this. Let me give an example of this method, just so you see it actually working. All right? And what I'm going to look at here again is this robust regression problem. So this is a non-smooth convex optimization problem. We have, basically our objective is the average over m data points of the inner product between ai and x minus bi. Okay, and on this plot, I'm showing you the error between f, my true objective, of my kth iterate, and f of x star, versus iteration. Okay? So if you look at this plot, you think, okay, well, the stochastic method and the regular subgradient method behave basically the same for a while, but then the subgradient method does a lot better. Right? But I'm not showing you, but how long does it take the stochastic subgradient method to get to here? Let's say m is 500. Actually, m in this case is 1,000. Okay? So each single step the stochastic subgradient method takes involves computing one inner product. Right? So in the time it took, so this line right here that I just drew is the time that it takes the full subgradient method to do one iteration. All right? So we're basically, before the subgradient method has even finished half of its iteration, the stochastic subgradient method has already basically gotten to accuracy, 10 to the minus 1, or 0.4, 0.3 or something like that. Okay? So before the subgradient method finishes even a single iteration, the stochastic subgradient method has some reasonably good behavior. And basically, the subgradient method finishes 2 iterations before the stochastic subgradient method has essentially, well, it's done about as well as it can. All right. Yeah, question?
I'm wondering why just a sample of size 1? Wouldn't a sample of size 5 have, a lot smaller standard error?
Yeah, that's a great question. So just so that it's on the recording. So the question was whether if we oversampled, if instead of in this slide taking just one example, we sampled say 5 or 10 or 20, whether that would do better. And the answer is that it's a little bit subtle. You can develop, so if my objective were smooth and say differentiable and 100, then you're right. That would you would get a linear improvement in the sample size that you were using up to a certain point. And so you want to use larger samples. When you have sort of absolute values and kinks like this function, you need to be a little bit more careful. But you can develop methods that will leverage that. Okay, I'm not going to talk about them, but later, in a few minutes, I will actually talk about methods that roughly build up approximations to your global gradient to reduce variance, and they have really great performance. So we'll talk about those soon. Yeah, it's a great question. Okay. The funny thing is here, so the point of this is that, when you have these sum structures or expectations of losses and things like this, well, the subgradient method, we can leverage this structure by just doing random gradients and taking random directions, and we converge eventually, right? And basically the entire proof is completely identical to the proof for the subgradient method, which is the neat thing, right? So remember, we write down this, and then we just kind of, drop the mic and walk away. If you're ever, giving a lecture to students, you can just do that and drop the mic and go. It's sort of a nice, it's the shortest lecture I've ever given. You do this in the first 10 minutes and then you just leave the class and let them figure it out. But yeah, so if we do this exact same proof, right, we look at this error between xk plus 1 and x star and expand the error, well, if you have a stochastic subgradient method, then basically the only difference between that and the subgradient method is that there's this mean zero error term here. Right? And so if I take expectations here, because we're doing things stochastically, we'll just take expectations. You stick an expectation in front here, you stick an expectation over here, right? And then the expectation, what is the expectation of this error term? It's 0, right? So this equals 0 in expectation. Okay? And once you've done that, well then that's exactly the same argument we have for the subgradient method. Okay, so nothing changes. These methods are essentially bomb-proofs. You really cannot hurt them because they use so little of your problem structure, except that you have a subgradient. Okay, so then you can give sort of the same types of convergence guarantees as you can give for the subgradient method, except you can sample things completely at random. All right. So that was sort of a blitz through the basics of kind of convex optimization methods, sort of first order, non-smooth, stochastic convex optimization methods. And what I'd like to do now is start talking about, well, let's talk about a few additional structures that we might be able to leverage that actually can give you substantially better performance if you're going to be implementing methods like these.
And quick question about the projected versions. So
yeah.
What is the cost of typical projections?
Yeah, that's a good question. So the question is, what about projections, and is it expensive to compute projections? Sometimes it is, sometimes it's not. So let's go back to that projection slide here. Okay, so I have us doing this projected gradient method where we compute this projection here. Okay, and in a lot of instances this is pretty cheap. So one example. Suppose that C is equal to the L2 ball, X such that the 2 norm is less than or equal to 1. Right? Then projections onto this set are quite easy. In this case, pi C of a vector Z is either equal to Z if Z is in C, and it's Z divided by its L2 norm otherwise. Okay? So this is an easy projection. With more complex sets, it gets a little bit more subtle. With the L1 ball, for example, let's do that example up here. So let's suppose that C is equal to X such that the 1 norm of X is less than or equal to 1. Okay, so let's say you were doing some kind of high dimensional or sparse estimation. You want to project to this set. In this case, the projection is a little bit more subtle, and I'm not going to completely specify it, but it's basically, it's X if X norm is less than or equal to 1. And otherwise, it's a vector with components, say, xj minus t. Oh, I'm sorry. It's going to have components which are the sine of xj times the absolute times xj absolute value minus some threshold t truncated at 0. Okay. And then this is of course a vector for j equals 1 to n. All right. where t is some kind of threshold. Now I'm not specifying this exactly, but basically you take each component and you shrink it linearly towards 0 until the sum of your components is equal to 1. Okay, so you can do this actually in linear time and figure out what the right thresholds are and things like this. So you have to be a little bit careful. It's a good question. But oftentimes, for a lot of the problems we look at, projections are fairly simple.
Okay, and in terms of convergence proof?
No, nothing changes. Nothing changes at all. Because, sorry, that's a good question. So the convergence proof, does anything change? No, nothing changes because of the following fact. That the projection of any vector x minus x star is less than or equal to x minus x star if x star is in C. Okay, projections take you closer to the set, that's all that's saying. Okay, I mean I can draw a picture of this right here, right? So if this is C, and this is x star, and this is x, right? If I project onto this set, I'm going to be closer to x star.
I was wondering if C can be non-convex and still you have something.
No.
Is it an if and only if it's not?
Okay, this fact, well, so it turns out that in finite dimensions, a set is convex if and only if projections are unique. Okay, so projections exist if and only if your set is convex. So in that sense, yes, we require convexity. We'll get to the non-convex stuff soon. Let's keep things, friendly. We don't want to be too adversarial quite yet. We'll get freaky soon, but not yet. All right. So stochastic gradient descent, simple, straightforward. But there are some bells and whistles that you might want to put on it. Say like if you have problems that have say more structure you want to talk about. So let's think of. I'm going to talk about two in particular, and one is trying to adapt to sort of the geometry of the problem you have at hand. So of course you've all seen pictures like these. Right? Somehow if you have an optimization problem whose level curves look like this, if you have a function whose level curves look like this, we sort of think of this as being ill-conditioned and it's kind of hard, right? Because if you were going to do gradient descent on this, you start here, you take a big step, you go over here, it goes over here, it goes over here, and it takes a long time for you to converge, right? If you just follow downhills. Whereas this is somehow it's easy, because no matter where you are, the gradient just points straight toward the optimum, right? And so somehow what we'd like to do for these stochastic type methods is be able to detect if we have a problem like this and transform it into a problem like this, right? So this is something we'd like to do, and the question is, can we do it? And here's sort of a structural property that occurs frequently that might motivate this. So let's think about a text data classification problem. All right, so suppose you have a problem and you're going to use binary word indicators. I'm going to give you a document. You're going to encode it with a bag of words. So just a 1 in a position where a word appears, zeros otherwise. In the English language, there's about 50,000 regularly used words. And if we think about using pairs of words or bigrams, then maybe say there's 3 or 4 million common ones. Okay? But in any given document I give you, a document has, say, 3 to 5,000 words. We're thinking you're essentially going to be left with about 1% non-zero entries in your data vectors. Okay? So this means, in this plot, these are features. And this is actually a data matrix of the Reuters RCV1 corpus. So on this axis, we're looking at different examples. And this is just a sparsity pattern of the data set. And you can see that, I guess you can't tell exactly what the percentage of sparsity is here. Up here it's a little bit dense, but basically, if you look across any one of these lines, you're going to get like 1 or 2 non-zeros. Okay, so this data is wildly sparse. And in this picture, what this looks like is this direction sort of corresponds to a sparse feature. There's somehow not very much information in the curvature of your problem. Okay, so this direction is a sparse feature, and somehow this direction is a commonly available feature. All right, so what might you do to be able to address things like this? Well, what we propose, so we being Yoram Singer, Elad Chazan, and I, was a method known as Adagrad, which is basically what you want to do is say, okay, I've got this problem which may have like vastly different behavior along different coordinates. Let's keep track sort of the geometry of the gradients that we observe throughout a run. All right, and let's maintain a diagonal matrix of these sum gradients. So basically, so if I look at this, this is to say that the, say, ith entry of this is the sum from t equals 1, say, up to k of the ith coordinate of my gradient squared. Okay? So I'm going to just keep around a matrix whose diagonal entries, are the squares of the gradients that I actually observe. Okay, so in this matrix, right, intuitively what's happening, a gradient of a dimension that I see a lot of, I'm going to have a very big weight in this matrix, and a dimension that I see very infrequently is going to have a very small weight, or even 0. Okay? And then instead of just doing, say, the classical stochastic gradient iteration, I'm just going to rescale my gradients here by this matrix to the, well, it turns out to the -1/2 is the right power. But basically I'm going to scale it in a way inversely proportional to the number of times the gradients have appeared. And so what's the intuition here? The intuition somehow is that, you pay attention, or your gradient method pays attention when infrequent features show up. Okay, so you want to pay attention if something infrequent shows up, and if you've seen, you've seen the word the 2,000 times in your corpus, then you probably know that the word the is not that useful, so you just kind of punt on it. Okay, you ignore it in your gradient updates. And this scaling, of course, is easy to compute. You can do this in linear time, and then you can prove this theorem if you feel like it, which is that if you let x be generated by the Adagrad updates, and we assume that our constraint set is a subset of -r, is a subset of the L-infinity ball, then basically Adagrad is in some sense optimal. It's sort of adaptive to the geometry in the right way. Basically you get this convergence rate, which is that after k steps, you have an error which is decreasing as 1/k times this infimum, where this infimum says I'm going to trade off basically sort of the geometry of my constraint set with this positive matrix A and the geometry of my gradients with this inverse matrix here. Okay, so if you look at this, you say, well, what does this mean? I mean, let's sort of punt on exactly how this might scale or things like this, but the point is that the usual stochastic gradient method is just A equals the identity matrix. Okay? And so here, by being a little bit careful and sort of saying, okay, let's actually do this kind of scaling and track things, it turns out that what you can show is basically you're going to automatically get this sort of optimal trade-off between your constraint set and the geometry of the gradients that you actually observe. All right? Now this is, you say, okay, theory, whatever. Is this actually useful? And the answer is that sometimes, yes, it is very useful. Sometimes it's not very useful. Right? But if you have structures that you can leverage, then you can really get some bang for your buck. So let me give, first I'll give a small example. So in this case, I have a 1,000-dimensional problem. This is just completely simulated. Okay, and I'm generating data vectors AI in R1000 and B in -1,1. And I'm going to have some x star equals 1. Okay, and basically I'm going to set BI is equal to the sign of AI transpose x star. Okay, and oh shoot, how did I've forgotten how I actually generate the data vectors A, so I apologize for that. Anyway, and then I'm going to flip 5% of these labels. So this is just a simple classification problem. And then I'm going to look at the hinge loss, which is this quantity here. Okay, so if we draw a picture of this, the point is that here's the hinge loss, and this is as BI AI transpose X increases, then the loss goes down. So if we have the correct, if we make a correct sign prediction, AI transpose X matches BI, then we have 0 loss. Otherwise, our loss increases linearly. All right, and what I'm showing here is a comparison of Adagrad versus the stochastic gradient method on this problem. And what we see is that they have similar performance at the beginning, but at some point Adagrad's performance starts to dominate. And with the right step sizes and the right type of problem, the right problem geometry, you can get better performance with these methods. So if you actually have a problem where sort of the natural geometry is somehow sparse data, dense predictors, then you want to use methods like this. All right, and so you can get, there's a gap here in performance, and you can actually run this on real problems. So here's an example. This is the Reuters text classification data set where you're given a news article and you try to predict whether it's about economics, corporate things, government, or medicine. Okay, and you can see that, in terms of test classification error, you're getting, say, maybe after a single pass through the data set with different stochastic gradient type methods versus AdaGrad, you're getting a non-trivial benefit by using these adaptive methods in terms of convergence and performance. Right, so if you have a problem where there's a structure you can leverage, say sparsity, dense predictors, then it's a good idea to be able to leverage it. All right, if there's no message you take home from this, it's, figure out what problem structure you have, try to nail that down.
It looks like it's, so since, as you said, if you take A is equal to I, it is the original, it's the original method. So it looks like you should always use AdaGrad, not the original version.
Yeah, so there's one thing. So the question is, it looks like you should always do AdaGrad since it gets this best possible A. So that's almost correct. And the reason that's not quite correct is because of something I glossed over. And that something I glossed over is this, right there. Okay, so I kind of cheated you guys a tiny bit. And I said my constraint set is in L infinity box, or contained in it, okay? This is a good idea if you think a dense predictor is going to have good performance and that's the predictor you want. If you want, say, like a sparse predictor, say because you're on high dimensions and you think there's only a few relevant features, or even if you think like L2 regularization is the right regularization or something like that, then this becomes a less good idea. Okay? So then it turns out that this is actually suboptimal in that case. Okay? And I punted on that because well, I don't know, we don't have time to cover everything. But yes, you want to use it sometimes, but it's truly dependent on the geometry of the problem you have. This is the case with almost all of these. Sometimes they're a good idea and sometimes they're not. So, and I'm trying to not sell you snake oil. I probably will. I mean, I am full of, I'm on video, I'm not going to curse. I'm full of horse patootie, I guess is a clean way to say that, but I'll try to tell you mostly true things today. Okay? All right. Right. Yeah, at Stanford I've had to ask them to stop videotaping me in classes, otherwise I get in trouble for the things I say. Yeah?
I guess the question on the test error here.
Yeah.
So do you have like direct bounds on the generalization error? Like the previous bound doesn't really show.
Yeah, you can translate a lot of these into bounds on generalization error, essentially for free. I'm happy to talk with you more about that offline. But essentially, in a lot of these stochastic optimization problems, where are we? Sorry. Optimization objective and generalization error are more or less completely equivalent. So basically, you show one gets small, then you get that the other one goes small. All right, so then let me talk about one last structural property that we can leverage. So this one is related to the earlier question about, what if we use multiple subgradients or something like that? Could we do better? And in the past, say, 5 years, I guess, we had this realization that often in machine learning, we solve problems which look like averages. Okay? I mean, maybe we already knew that we solved problems that look like that, but we had this realization that we could really nail them down. Okay, and so this is, so the idea here is that we can actually more accurately approximate the gradient of f using the fact that we have this finite sum structure. And then we can actually get faster convergence than just, say, stochastic gradient methods would allow. And this is work due to a number of folks, Rui Johnson, Tong Zhang, Aaron DeFazio, Francis Bach, Simone Koch-Julien, and Shai Schwartz. And I'm sure I'm missing other people in these lists because a lot of folks have worked on this. But let's talk about, so I'm only going to give you the algorithm and then a tiny bit of intuition. So the basic idea for these algorithms is they sort of work in epochs. Okay, there's an outer loop and an inner loop. And in this outer loop, what we do is you basically keep around the true gradient of your function. Okay, and then there's this inner loop, where in the inner loop, essentially you run stochastic gradient, but not quite.
Okay, so you don't quite run the stochastic gradient method, because what you do is, for some number of steps t, you compute a stochastic gradient by choosing an index uniformly at random, at whatever your current iterate is. But then, instead of just going in the negative gradient direction, what you do is you basically keep around the sort of global gradient that you've been computing, and you just sort of swap out your new gradient for the old gradient, okay, in that sum. So this is somehow a reduced variance version of your stochastic gradient. And then the neat thing with these problems is, and again, I'm not going to delve into this too much just so that you've seen it. Basically, with appropriate settings of t and then this step size alpha, you get a convergence rate which is linear. Okay, so this is what we call a convergence rate. Basically, in every epoch, we get a constant improvement in the gap of our objective values. All right, and this constant is essentially independent of sort of problem conditioning and all sorts of things. It's just this is just a numerical constant. It's like 3/4 or something like this. All right, so this is a sort of a remarkable result that by doing this kind of reduced variance calculations, instead of computing stochastic subgradients, we correct them slightly with the global gradient. We can get way faster convergence of our iterates. And if you actually run these, you really do see improvement. So here's just a simple example of linear regression, okay? Now you might think, okay, John, this isn't that impressive of an improvement, all right? So what I'm showing here is this axis is, of course, this is time, essentially. And this axis is the gap between your current iterate's objective value and the best objective value. And SGD is this green line with triangles, and you can see it improves a little bit more quickly, and then it sort of plateaus. And stochastic variance reduced gradient does better. But what I'm not showing you in this plot is, so this is best SGD. Okay, so I ran the stochastic gradient method with 45 different step sizes, and I took the best one of all of them, okay? Which means that this line took 45 times as long for me to get as this line. All right, and if you look at other versions of stochastic gradient method with different step sizes, I mean, they'll be up here, or kind of here, or here. I mean, who knows? If some of them go over this way, which is the wrong way. So the point is that, if you actually have, this finite sum structure right there, and you leverage it, then these methods can be extremely powerful. All right. So once again, what you see is that by being a little bit clever, saying, okay, I can actually reduce my variance by doing this type of calculation for these things, then I can get really good performance and really good behavior, really good convergence guarantees and good practical performance. Okay. So the take-homes from this part. Sometimes, 1, really dumb methods are competitive. Stochastic subgradient methods, pretty solid. 2, knowing something about your problem can help a lot, and leveraging the problem structures that we have can be really important. And some of the structures that we talked about were, stochastic structures, finite sums, and sort of sparse data or problem geometry. And nailing that down can be really useful. All right, so this is the end of part 1. And
just a quick question about
yeah.
The point 2 and 3 are not specific to projected gradient methods, right? I mean, these are for even the descent methods.
I mean, this is true sort of always, of course. The more structure you can leverage, the better you're going to be able to do. And the question is, can you nail down what those structures are? And so for these optimization problems, finite sums is one structure that we've seen a lot of bang for our buck nailing down. 2 is sort of being able to adapt to the geometry of the problem that you see. And 3 is the fact that, well, subgradient method's super slow, but they handle noise very, very elegantly. Okay? And so figuring out kind of what you can really leverage in these problems can be extremely useful, both in theory and for practical purposes. Okay. All right, so now I want to start part 2 of this talk, which is in structures in non-convex optimization. So the point here is now we're going to depart a little bit from the well-worn track of convex optimization, with which a number of you are already familiar, to talk about problems with structures. They're not quite convex, but they're still amenable to elegant solution approaches. All right, and you can another way to think about some of this is we can often leverage stochastic or statistical structure in problems to turn sort of nominally hard non-convex problems into easy ones. Now, I'm not the first person to say this. I mean, this is a sort of body of work that's been growing in the last 5 years or so. And we'll talk about who's been doing it. But the point is that oftentimes, the fact that we solve statistical and statistical learning problems makes sort of what look like NP-hard problems not that hard. All right, and we can prove that they're not that hard, and we can also, get really practical algorithms for these things. So let's talk about the generic. This is as generic as I'm going to get. We're going to nail this down shortly. The generic type of problem that I want to think about is what I will call a semi-convex function. Okay, so a function is called semi-convex if there is some lambda, any lambda, as long as it's finite, where if I take f and map it to f of x plus lambda times a quadratic function of x, it becomes convex. So if a function, if I add a big enough quadratic to it, becomes convex, then I call it semi-convex. All right? Okay, so that's the generic definition of the type of problems I'm going to look at. Now this is way too broad for us to actually think about, but let's just talk very, very briefly about why might this even be a useful notion. Okay, the reason this is a useful notion is because we can at least develop methods that go downhill on these things. Okay, that's basically that's the least thing you could ask for. So we can develop methods that will go downhill on these, right? And the way we can do this is what's known as the proximal point algorithm. And so this is what sort of justifies a focus on these things. All right. So what we can do, because this is now a convex problem, I can minimize it, right? I mean, I could run subgradient descent or something like that, and I could get to the minimum of this function. Even if it doesn't have a lot of structure, at least it's convex, I can go downhill on that stupid thing. Okay, so what I can do is I'm going to iterate xk plus 1 is equal to argmin of f of x plus lambda on 2 x minus xk squared. Okay? So this, basically I can solve a sequence of convex optimization problems, right? So this is convex. So at least, nominally I can solve it by a subgradient method. And this is also a descent method, because what I see is that, of course, if I chose xk, then this would be 0 and this would be f of xk. So I always have that f of xk plus 1, plus lambda over 2, xk plus 1 minus xk squared is less than or equal to f of xk. All right, so at least I can go downhill on these functions, which is, okay, I mean, that's a pretty sort of dumb guarantee, but look, if you can't even go downhill on a function, it's going to be tough to minimize. So this is somehow the set of problems where it's still reasonably easy to go downhill on these problems. All right. Okay, now you guys should be looking at me like, John, who cares? How in the world would you tell if you have a problem like this? What's the point? Well, so the nice thing is there are a few sort of concrete classes that have this structure, and then we can nail down things and develop interesting algorithms for it. All right, and here are the two that I'm going to talk about. So, actually, I'm only going to talk about one of them, but here are the two that I find kind of interesting. And one of them is any function that is smooth, meaning say it has two derivatives, is at least locally semi-convex, right? Because I can do a Taylor expansion, right? F of y is f of x plus the linear term plus a quadratic, right? Where here, because of, by Taylor's theorem, x twiddle is just between x and y. Whoopsie. There we go. Right? And clearly, if I add enough, this matrix, I don't care what it is. If I add a big enough multiple of the identity to it, it will become positive semi-definite. Right? So your second order expansion, if your Hessian is positive definite, we know you're convex. So so certainly grad squared f of x plus lambda times the identity is positive semi-definite for large enough lambda. All right. Okay. So at least smooth functions are semi-convex. Okay. That's great. So I mean, you guys already knew how to go downhill on a smooth function. You take the gradient and you go downhill. The sort of more interesting class of problems, which is generically semi-convex or kind of close to being convex, or what I'll call compositional optimization problems. And this is a nice class with which you are likely not that familiar, I would guess. And this is to say I want to minimize a function f, which is the composition of a function c, which is smooth, okay, and I'll define smooth presently, and h, which is convex. All right, so I can compose a smooth function with a convex function, and I'm going to get a semi-convex function. And when I say smooth, I mean that c smooth is equivalent to gradient c is a Lipschitz function. All right, so the gradient of my function c is Lipschitz continuous means that c is smooth. And I'm not going to prove to you that these are semi-convex, but I'm going to talk about a lot of nice things that we can do with them. Well, let's sort of try to motivate this problem class and try to understand how we can leverage this sort of kind of funky compositional structure, both for modeling interesting phenomena and for developing interesting optimization algorithms. All right? Okay, so let's dig into this. So this is our problem that I'm going to more or less spend the rest of this tutorial on, because I think it's an interesting family of problems that are plausibly broadly useful for a lot of different problems we have in statistics and machine learning. Okay, so we're going to minimize a function f of x where h is convex and c is smooth. All right, so the motivation for these types of methods comes from what's known as the exact penalty. All right, so let's just say I have a generic optimization problem, and I want to minimize my function f of x subject to some constraints. Say I want x to belong to some set, capital X. Okay, then it turns out, and this is a theorem and you can prove this, is that for large enough lambda, the minimizers of this function are identical to the minimizers of f of x plus lambda times the distance between x and my constraint set. Okay, so here, let's looking at this picture, right? So this is my set x down here on the bottom. So this guy right there is x star, right? Okay, so this is a non-convex optimization problem. Clearly, this is not a convex objective. And I'm going to claim to you that if I add the distance from points to x to this, eventually these are going to become the same problem, have the same minimizers and everything. So let's do some pictures. So okay, so here, I've just added the distance from x to my objective. So we went from this blue line here to this new blue line, which now you can see there's a tiny little kink, right? But this still has different minimizers than the constraint problem. But if I add a really big multiple of the distance, what you can see is that we went from, yeah, sure, we don't have any active constraints, but right here, this is both the global minimizer of the constraint problem and the unconstrained problem. Okay? Okay, so if we add a big enough multiple of the distance to our constraints, then we're in good shape. Now, so what? What does this have to do with composition of convex functions and smooth functions? Well, this is what it has to do with composition of smooth and convex functions. So suppose I just had some kind of generic constraints. I want some function c for constraint, to be equal to 0. Okay? If c is a smooth function, well, what I'm going to do is I'm going to just take the norm of c. Who knows? It doesn't even matter what norm. The point is that the norm at 0 has this pointy kink thing. And if I add a big enough lambda, then these two problems are equivalent, because it's going to look like this. Okay? The only minimizers of this are going to be where c of x is equal to 0. All right? And now look at this. What does this look like? So a norm is is a norm convex or not? Norms are convex, right? We agree? Okay, good. So we agree that a norm is a convex function. So this all of a sudden looks like a composition of a smooth with a convex function where h of z is just equal to the norm of z. All right, so sort of generic non-convex constrained optimization problems we can write as compositions. I mean, we can replace them with sort of compositions of smooth and convex objectives. So this is one of the major motivations for these types of problems, right? Okay, yeah, this is just saying what I just said. Okay, so, sorry. So another motivation which I think is compelling, and perhaps more compelling for a lot of statistical applications and a number of engineering applications, is nonlinear measurements. All right, so let's suppose, and this is where we see that
I'm pretending to be an engineer, we have a signal x star in Rn, and we're going to have some measurement vectors ai. Okay, and in linear regression, we usually assume we observe, ai inner product with x plus noise. But now, what if there's some nonlinearity that mitigates our observations? All right, say some function phi. It's not linear, but it's smooth. Right? Then what we observe, instead of ax plus noise, we observe phi of ax plus noise. Then a very natural objective for trying to fit these things is I'm given a data set, given, say, a set of pairs ai, bi, for I equals 1 up to m. Right? I just say, okay, well, the natural loss for this is, look, I just write down phi of a comma x, minus bi and squared. Right? And this is clearly, a convex function. H of z is equal to, 1 on m times the 2 norm of z squared, and c of x is equal to just the vector phi of a1 transpose x minus b1 dot 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 phi of am transpose x minus bm. Right? So this is, these types of nonlinear measurement problems are very natural scenarios in which this kind of compositional structure, composition of a smooth function, of a convex function, in this case the square, with a smooth function, in this case the error in our measurements, is really natural. So this leads to nonlinear least squares problems, which have been studied for a while in the optimization and statistics literatures. An even more sort of, where this is a real engineering problem, this really does occur. We do take these measurements, we want to solve this problem, is what's known as the phase retrieval problem. So in the phase retrieval problem, what happens is you have some kind of molecule, which in this case is the sample, and this is what's represented by x, and it has a structure that you want to find out, and this is x star. Okay? And what you do is you shine x-rays at it. Okay, these things go through a particular sort of phase plate. And then what we can measure at the end of the day is we have a sensing apparatus over here, and what we measure actually is, well, it turns out we measure the Fourier transform of this light going through our sample, except we can't actually measure the Fourier transform. Because of limitations in our measuring devices, all we can observe are the magnitude of the signals we're observing. Okay, so we lose all, in the complex case, we lose all phase information, which is to say rotational information. In the real case, we just lose the sign. So in the real case, honest to goodness, all you can observe is essentially the inner product of ai with x squared. All right. So and this is a real measurement procedure, and this is really what you actually observe. Okay. And maybe sometimes there's noise, sometimes there are corruptions, etc. Okay. But then in this case, sort of the most natural objective you could come up with is, well, let's just look at the error between ai and x squared minus bi, the observations, and we'll just take the absolute value of that. Okay, now this, you look at it, what is this? It's a, what words am I about to say? Somebody.
Composition of convex and smooth function.
Right, it's a composition of a convex and a smooth function. Right, so this has this natural compositional structure, and it pops out instantly from, your measurement process. Okay? All right, so now, I hope I've convinced you that these are sort of natural, nice problems, and so it behooves us to think about, okay, what is this is a structure that plausibly could come up in a lot of scenarios. It behooves us to generate, to develop schemes that we might use to optimize them. So, let's talk broadly, temporarily. Like, how do you solve optimization problems? Just sort of generically, what do we do? Well, what we do is we sort of do this two-phase thing, where in the first step we build some kind of good but simple local model of our function f. And then in the second step, we minimize this local model, or maybe we regularize it when we minimize it. All right? And so let's first talk about gradient descent. So what does gradient descent do? Gradient descent builds a first-order model. So what we do is just to set notation, sorry. If I have a subscript x, that means I'm modeling my function f around a point x. Okay, so gradient descent does a first-order expansion. It says I'm making a first-order or a linear model of my function. So looking here, this point right here is x. Okay, and then this red dotted line right there is f sub x of y as a function as y moves
left to right. Okay, so gradient descent makes a linear model, and we minimize, well, we often regularize that, and then we minimize it. And Newton's method, of course, makes a second order expansion, right? You model your function with a quadratic by doing a two-term Taylor expansion. Okay. Now, what are we going to do for these composite problems? Well, instead of a first order model or a second order model or anything like that, we're going to make a convex model of our problem. All right, and we're going to iteratively minimize that model. And how we do this is we say, well, this could potentially have, it could be non-smooth, it could be all kinds of weird, right? Because H is just convex. It could have kinks, it could do all sorts of weird stuff. So what we do actually is what we're going to do is we're going to linearize the inner part, C, because C is smooth. So Taylor approximations to it could potentially be pretty good. And so what we do is we say, hey, you know what? F of y is approximately equal to, so I'm basically going to just do a Taylor expansion of C around my point x. Okay? And once we do that, well, Taylor expansions are accurate to say second order, right? Because that's how Taylor expansions work. So this is basically equal to C of y plus some quadratic error term, or plus or minus some quadratic error that I'm just going to punt on. All right, and so basically I'm just going to define my model for my function f at a point x is just, I'm going to leave the outer part completely the same because it's convex and I don't care. I'm going to linearize the inner part. Now what is a convex function of a linear function is still convex, right? So now I have a convex function that's a pretty good model of my maybe originally non-convex, non-smooth problem. So this is an old idea, probably due originally to Jim Burke, but folks have been restudying this and renegotiating some of these things recently. All right. So let's do an example. So this is my favorite example, and it's sort of the phase retrieval example at a small scale. Okay, so here, let's look at our function f of x is x squared minus 1, and then I just take the absolute value. Okay, so this is certainly absolute value of a quadratic has this compositional structure. All right, so this function looks kind of like a bat, I guess, right? And it's convex over here. This region we're convex because it's nice and curved downward. This region it's kind of convex, and then there's a kink, and over here it's concave. Right? So this is kind of an annoying function if I just handed you this, you'd be like, that looks annoying, no thanks. Right? It's non-smooth, it switches from convex to concave, that sounds like a huge pain in the tail. But this modeling that we can do of it actually makes it perhaps not so bad. Right? So here, I've done my approximation. This is my point x, and I did a first order approximation to the smooth part, the quadratic, and then I stuck an absolute value on it. I got that. And if we set our points closer to one of these kinks, then we get actually quite accurate models of sort of the geometric structure of our problem, right? All right. And so what that does is that leads to these very natural methods, which we'll call the Prox linear method, which is to iteratively, you basically form a regularized convex model of your function, and then you minimize it. Okay? That's all you do. You just say, okay, hey, I'm going to linearize C and treat that as my function. I'm going to add a little bit of a quadratic penalty here so that I don't jump too far away from my local approximation, so I know I'm still doing something reasonable. And I'm going to just minimize this, and I'll just repeatedly do this. Okay, so I model my thing as convex, I add a quadratic, I keep going. All right. So let's give an example. Let's run through an example here. So I'm going to do the absolute value of x squared minus 1 function again. So the bat function, I guess we'll call it. I don't know, it just looks like Batman to me. The Batman sign somehow. Does anybody else see that and think Batman? It was the first thing I thought when I saw it. I don't know. I watched too many Batman cartoons as a child, I guess. But anyway, so we're going to do the Batman function. And so we start off, let's say we just start off, and here's our initial point. There's x0. Okay, so we have this red dotted line as my convex approximation. So this is f of x0 of x. All right, and then I add a quadratic to give me this blue line here, and I minimize it. Okay, so we minimize that, and then we're going to zoom in a little bit. And now my error, it turns out, is 0.3. And so we zoom in and we do this again. We have, here's x1. And we make
this is fx1 of x, and then we add a quadratic, we minimize it to get there. And then we repeat this, and all of a sudden our models start looking quite good, right? At least locally, we're getting really good. And actually, you can see the errors down here at the bottom. You'll notice that they're going down really quickly. Okay, this is like 10 to the minus 4, 10 to the minus 8 in 5 steps. All right. So this is how this method works. You know, we take a nominally ugly function, we make a convex model because we can, because it's this nice compositional semi-convex structure, and we minimize it. All right. Okay, so that's the convex composite optimization schemes. Now, so sort of at least generically now, we know we can kind of descend on these functions and you can prove that they will converge to stationary points and all sorts of things like this. The interesting question, I mean this is already I think interesting because it's sort of a generic structure you can exploit that maybe you hadn't thought of before. The interesting question is when maybe, you know, do these really, really work or provably work or really like solve the statistical problem you care about? Okay, so let's try to make some connections between these and statistics or machine learning and try to understand what's going on here. Basically, the insight is that in a lot of statistical problems, there is sort of enough signal to overcome kind of the difficulties of non-convexity. And often, for a lot of problems, you can actually prove things like that the only stationary points of your objective are actually global optima. Okay, you may have a wildly non-convex function, but there are only certain stationary points, and all of them are equally good. All right, and this is, you know, if you can show this, now all of a sudden you've got everything you want. You've got a nice optimization scheme. You know all the stationary points are global optima, and life is good. So this line of work probably started with Andrea Montanari, and I don't have a citation, I'm sorry. Andrea Montanari and his students Keshavan and Siwong O, and then Pulling Low, Martin Wainwright, John Wright and his students at Columbia, and some other folks. Okay, so let me just give an example of where this happens. And
I had a quick question. So
yeah.
Just to understand, so this method converges, the method that you showed with smooth composition of convex and smooth, it converges to stationary points.
Mm-hmm.
So I'm not familiar with non-convex surfaces, but let's say I just did gradient descent, where do I, like, they go to some points, what are those points?
Well, so if you have a composition of a convex function and a non-smooth function, it's not necessarily smooth. Right, I mean,
okay,
clearly...
I take subgradients, then, okay, I will go anywhere.
Well, so what's a subgradient of these functions?
Okay.
They don't even necessarily exist. So, you know, you don't know if you wouldn't know if you were going downhill or uphill or which hill. I mean, it could get weird. So that's why you want to, you know, this is why these structures are kind of important, because you say, oh, this has this nice compositional structure, which pops out pretty naturally. And
Okay,
now
so if I
can,
namely apply gradients with some fixed steps, I'll be totally off.
well, maybe. You just, I mean, it's unclear. You know, it may work sometimes, but it may not. So it's very challenging to figure out what's going to be happening. And at least with these, you can actually, you know, they come with guarantees that you will converge to things, and you can actually test whether the method is converged. You can do all sorts of stuff, which is a nice, you want to be able to test when you're done.
Okay.
Right? And these come with tests to be finished. All right. Okay, so let's, but yeah, so let me, now that we sort of described these methods, let me dig in a little bit and help you sort of understand what do I mean when there's enough signal to overcome this like issue of non-convexity. All right, and I'll go through a fairly simple example of this, and just to give you an idea of the flavor of things that one can show, and you know, then if you guys are amped up about it, there's a bunch of references at the end that are totally worth digging into. So let's think about the nonlinear regression problem. So in this problem, you know, instead of linear regression where we have AIX plus noise, we're going to have some phi function where here I'm going to make my life really simple and assume phi is monotone increasing, which is to say, I'm even going to be really lazy. We're going to say phi prime of t is greater than or equal to some c greater than 0 for all t in R. Okay, so I'm going to be super lazy. There's some monotone transformation I applied to my data. Okay, but it is nonlinear. And so now I'm going to try to understand what happens when I have this, and can I find
the X that actually generated my signals. Okay, so these ideas I'm stealing from Songmei and Yubai and Andrea Montanari's work. But let's say we have BI is equal to this nonlinear transformation of AI transpose X star plus noise. Okay? And we can extend these results to when these models aren't quite true and things like this, but let's make our life simple just to see what's happening. All right, so then my objective is going to be this very natural composition of a quadratic error with my measurement, a quadratic applied to my measurement errors. Okay, so h of z is equal to 1/2 z squared, and I look at expectation h of, phi of ax minus e. Okay, so this is a composition of a smooth function and a convex function. Then in this case, if I compute gradients of this, well, so note that b is actually equal to phi of inner product between a and x star plus whatever noise there is, right? That's because that's what we're actually observing. Then if we actually compute these gradients, well, you just do you just apply the chain rule. So the derivative of h squared is just z, or z squared is just z. So that's this term, and then there's the phi prime of ax, and the derivative of ax is a. Okay, so we can compute gradients. Good job, John. You remembered first year calculus. That's all I remember from first year calculus, but that's evidently all I need. And now what we can do is ask, okay, is this gradient giving me enough signal to do something interesting? And what I can show actually is that if this is 0, then we're at x star. So let's go ahead and do that, okay? So the way to do this is this clever idea, which is to take the inner product between the gradient of f at our point x and the error in x minus x star. So if I just do this, well, let's plug things in. I'm going to get e of the quantity phi of a comma x minus phi of a x star minus the noise times phi prime of a x, times the inner product of a and x minus x star. Right? But we've assumed that, so I'm going to be really lazy now. I've assumed that phi prime is positive because it's going to be, it's some monotone, maybe not like linear, but some monotone transformation. And so this guy is going to be greater than or equal to c greater than 0. Now, what about this noise term? So this is mean 0, so I'm just going to punt on it. Okay, so this in expectation is 0, so we can just ignore it. So this thing, expectation of c is equal to 0, so let's get rid of that. Okay, so goodbye c. And now there's this last bit. So phi of a comma x and phi of a comma x star. Right? So note that this term is greater than 0 if ax is greater than ax star, and it's less than, well, greater than equal to, and less than or equal to 0 otherwise. Right? So it has the same sign as the inner product of a and x minus x star. Okay, so this whole term, this whole objective is now greater than or equal to the expectation of phi of ax minus, excuse me, phi of ax star, and I can even take absolute values of this times c times ax minus x star, absolute value. Okay? So basically, and then this term, this inner term right here, because this thing is a monotone function, is actually greater than or equal to c squared times the expectation of x minus x star transpose a transpose x minus x star. Okay, and if you look at that, well, that looks a lot like a quadratic distance between x and x star. Okay. So I mean, this is easy because there's a beautiful axiom that Jim Burke told me, which is that, John, if you make stronger assumptions, you can prove stronger things. So this is an example of that axiom at work. I made strong assumptions, I can prove strong things. But the point is that this is 0 if and only if x is equal to x star. Okay, so this equals 0 if and only if x equals x star. All right? And so now we know that the only stationary points are when we have actually gotten to the optimum. All right. So I'm going to punt on this gradient domination thing. Let's not worry about it. But the point is you can actually get fast convergence for this. And now, let me kind of spend the last, Gal told me I had 5 minutes, I'm going to take 10 because we started late and I had stopped listening to him when I was, I don't know, 23, 24. Let me talk about phase retrieval problems. So these are, we're going to do some real actual imaging applications here and try to nail these down. So let's take a look at these. So in this case now, this is not as simple anymore because I no longer have a monotone transformation of my data and I'm going to have some noise which may make things a little rough. But let's say that I have signals bi equals the inner product of a and x star, so this is my true signal, but I can only observe their magnitude, and then periodically, let's say I have an equipment failure and maybe there's some kind of just arbitrary corruption when my equipment or measurements fail. All right? Then let's write this down as a natural compositional objective. Well, because this could be arbitrary corruptions, we want to be a little bit robust, so we're going to use absolute value, L1 errors. That's what we typically do in robust regression. And I want to solve this minimization problem. So minimize ax squared minus bi, absolute value. All right. And of course, this is in this composite objective framework. So the cool thing is that in this case, under sort of nice enough measurement models, we can actually give a convergence theorem for this composite optimization problem. And I'll not worry too much about the conditions, but the point is that there's some kind of growth condition where x away from x star has fairly large objective value. Let's not worry about this product temporarily. We have good local models because we do nice convex models of our objective function, so they're sort of quadratically, their error is only quadratic in how far away we are from x and y. And then we have a reasonable initialization procedure, okay? Skip all that. Then it turns out that under reasonable measurement models for these types of retrieval problems, remember we're shooting lasers through a molecule, then you run this composite optimization problem, this composite optimization method. If I let the distance between x and x star be the minimum of x minus x star and x plus x star, and then you iterate this sort of convex approximation, minimize, convex approximation, minimize. The distance between your kth iterate and the true signal, because of course we can't tell what sign the true signal has, so we can only give it up to signs, is going to be less than or equal to the distance from your initialization point to the true signal to the 2 to the k. Okay, so that's not 2k, that's to the 2 to the k. So for all intents and purposes, so assuming that this is less than 1, if k is 5, then we've converged. Okay, so 5 steps, 5 convex problems, and you can solve these fairly non-convex, non-smooth, weird optimization problems. All right? Because, if k is 5, that's anything less than 1 to the power of 32 is pretty close to 0. If you're really worried about it, make k 6. Right? Then you're taking something to the 64th power. Right? So you solve, okay, 6, fine. 6 iterations and you solve these things. Right, you solve 6 convex optimization problems, no tuning parameters, and you call it a day. Rather than digging in too much into the analysis, let me just, because I think I've accomplished more or less what I wanted to accomplish today with you guys, which is that if you model things well, you can minimize them even with these wildly non-convex problems. The point is that a lot of natural measurement models, as soon as your number of measurements is sort of linear with your signal size, then you can get these types of good convergence behavior. But let's go through some examples and see if this kind of idea actually works, right? Because I told you, I like proving theorems, but I also like to do useful things. Let's see if I'm full of shit or not, right? So let's do a couple of things. So first, I'm going to just start with just random Gaussian measurements. This isn't really a real application; it's kind of a simulation. But let's just see what happens, okay? So I'm going to just take my data vectors to just be IID normal 0, 1, and I'm going to not allow any noise. So we're going to get really exact measurements. And so we want to see, do we recover X star? Okay, I'm going to compare to some other procedures. Don't worry about what exactly they are. They're sort of the best state of the art. And it turns out that there's a threshold. You need 2n measurements n is our signal size, our dimension, to even guarantee that the solution is unique to these problems. Okay? Generically, you need 2n measurements. We're going to look at the probability of succeeding. And what you see is that as this ratio of m over n increases, when m over n is 2, sorry, I can't see this. Okay, that one. When m over n is 2, we're getting basically 90% recovery of the true signal. All right? So that's, 100% is possible here, but it's an NP-hard problem. Right? So this is actually working, at least for these simulated problems. All right. Let's not worry about that too much. It turns out when we corrupt the measurements, similar behavior holds. We get recovery a lot, quite frequently. Here's kind of a more interesting problem, which is closer to the real engineering systems that we actually do see. So here, I'm going to take 16 by 16 grayscale digits, and what I'm going to do is apply Hadamard transforms, slightly randomized Hadamard transforms to these digits, and then destroy all sign information. Okay, and then I'll also corrupt a few of my measurements. Okay. What we want to see is whether these composite optimization procedures, sequentially solving convex optimization problems, actually works. So on the left, so we did this with a couple hundred different images. On the left is the true image. Then we corrupt it, and then there's a particular initialization we use, which for the number 6 is right here, for the number 5 is right here. And on the right is the solution that you get by solving these composite optimization problems. Right? And I don't know, I think you guys can agree that these look the same. Right? So you really are nailing it. And these things have extremely high success rates. So you can corrupt, say, even up to basically 10% of your measurements, and you're still getting a success rate of something like 95% recovery of your original images, even if you're corrupting a lot of things arbitrarily. And for the last little picture, these also work at scale. Okay, so this is an image. It's a colored image, and so it's about 1,000 by 1,000, which means the signal size is 4 million. Okay, so we have a 4 million dimensional problem, and I'm taking 3 times. That's supposed to be 2 to the 22. Sorry, 3 times 2 to the 22 Fourier transforms of this image. All right, and then I'm destroying their magnitude. So this is where we initialize this method. So can anybody tell me what this is going to be?
Smiling face.
What's that?
Smiling face.
Smiling face. That's a pretty good guess. Right. So this is where we initialize it, and this is where it ends up. Right. So it was a rhinoceros, but you were close. Right. So yeah, I don't know. I just found some child at the playground and took a picture. And then they asked me to leave. I don't know why. You guys don't do uncomfortable humor. No, that's actually my daughter. So anyway, but these things, if you happen to have corrupted Fourier transforms of images of your kids and you want to recover them, you can do that with, maybe something weird happened to your iPhotos library, and it just was like, hey, we Fourier transformed everything in your image library. Sorry. Then we took only the magnitudes. Good luck. Anyway, but the point is, these things, they're nice, they're good models, and you can really solve things in practice. Okay. All right, so let me kind of conclude here, and I hope, clearly we couldn't get into too much depth for a lot of these things, but the point is, I think there are broadly interesting structures for a lot of non-convex optimization problems that you can still approximate with nice convex things. Okay, and I think these are potentially really powerful modeling tools. We're working on them for solving different types of low-rank matrix problems and sensing problems like this. You can use them, it turns out, for some graphical model structure problems that I'm happy to chat with you a little bit about if you're keen. Also, statistical modeling allows you to actually say really concrete things about solutions of sort of non-trivial, non-smooth, non-convex, nominally NP-hard problems. There's still a lot of work to be done for these things in terms of getting them to really, really work at large scale, because we, of course, have lots of large-scale problems. But I think, this is, I think this is going to be a fruitful area and worth thinking more about as these sort of generic structures that we can leverage for non-convex and other types of optimization. So, whole pile of references. Thanks for your attention. Happy to take more questions. And yeah, that's it.